Hi everyone! In this video session, we are going to discuss together the report writing guidelines for experiment 5. The title of this experiment is Simple Harmonic Motion. Please write your experiment report in the lab report writing section provided in the physics practical workbook. The learning outcomes of this experiment are: firstly, to determine the acceleration due to gravity g using a simple pendulum. Secondly, to investigate the effect of large amplitude oscillation to the accuracy of g obtained from the experiment. A warm reminder, all the values shared under the observation are just for your reference to ease in explanation. You are not allowed to copy and use the values for your experiment report. Any values found the same in your experiment report are against the scoring rubrics, as no plagiarism is allowed. Another warm reminder, you must write your own lab report. You are not allowed to copy your peers' experiment report. Any doubts found in the originality of your experiment report are against the scoring rubrics, as no plagiarism is allowed. Observation. Swing the pendulum bob at an angle less than 10 degrees from the vertical. In this experiment, we fix it at 9 degrees. You may use any other angles instead of 9 degrees as long as it is less than 10 degrees. Then measure the time for 20 oscillations. Make sure all the column headers are labeled properly with physical symbols and units. The number of decimal places for primary data must follow the sensitivity of the instrument used. The length of the string was measured using meter stick, and the sensitivity of the meter stick is plus minus 0.1 cm, and it consists of 1 decimal place. Therefore, the length of the string that recorded also consists of 1 decimal place. The time for 20 oscillations was measured using stopwatch, and the sensitivity of the stopwatch is plus minus 0.01 second, and it consists of 2 decimal places. Therefore, the time recorded in the data table also consists of 2 decimal places. And the average time for 20 oscillations calculated also rounded off to 2 decimal places, same as the sensitivity of the stopwatch. The period T is the time taken for one complete oscillation, and it is obtained by dividing the average T with 20 oscillations. Then we square the period T in the last column of the data table. Both the calculated values of T and T squared are rounded off to consistently 2 or 3 decimal places. Roman 2. Calculation of centroid point. The centroid point is the mean position of all the data points to be marked on the graph, especially on a straight line graph. Therefore, we need to calculate the average value of the x-axis and the y-axis, which is the average L and average T squared respectively. In general, the coordinates of the centroid point is written as average x and average y. We are plotting graph of T squared against L, where T squared is for the y-axis and L is for the x-axis. Therefore, the centroid point of this experiment is written as average L and average T squared. Remember to show the calculation of centroid point for average L and average T squared in your lab report. Therefore, the coordinates of centroid point for this experiment is 65.0 and 2.69. Remember to mark the centroid point on the graph of t squared against L, then circle it to differentiate the centroid point from other data points. Roman 3. Plot graph of t squared against L. Appropriate scales are used for both x and y axes. For example, in a multiple of 1, multiple of 2, multiple of 5, or multiple of 10. The size of graph is at least or greater than 50% of the graph paper. Then label the y-axis and the x-axis correctly with units in brackets. Write the title of the graph as graph of t squared against L. The calculated centroid point is marked on the graph paper and circle it. Then followed by the other 6 data points 1, 2, 3, 4, 5, and 6. A balanced best fit line is drawn through the centroid point and as many data points as possible. What does it mean by a balanced best fit line? A balanced best fit line is drawn through the centroid point and as many data points as possible. A straight line is drawn passing through the centroid point and 4 data points. However, there are 2 data points which are deviated from the best fit line below the centroid point. There is one on the right-hand side of the graph and the other one on the left-hand side of the graph. The distance deviated from the best fit line for data point 1 on the right-hand side of the graph is almost the same as the distance deviated from the best fit line for data point 2 on the left-hand side of the graph. Therefore, these 2 deviated points are almost balance each other. And this is a concept that we use to draw a balanced best fit line. For the calculation of the gradient of the graph, we need to draw a triangle of gradient. The sides of the triangle of gradient is at least 8 cm in length. Then we label the coordinates of the triangle of the gradient on the graph. Roman 4. Determine the gradient of the graph. The formula of the gradient is given by y2 minus y1 divided by x2 minus x1. y2 and y1 are the y coordinates of the triangle of gradient, whereas x2 and x1 are the x coordinates of the triangle of gradient. When we want to substitute the values of y and x, how many decimal places should we write for each of the entry here? Let's continue here. For the operation of addition and subtraction, the number of decimal places of the x and y entries must be consistent. How many decimal places shall we consider for the x and y values? It depends on half of the smallest division of the scale used for both x and y axes. What does it mean by half of the smallest division? How to look for the half of the smallest division for the y-axis? Please refer to the enlarged diagram on the right-hand side. There are 10 divisions between the value of 0 and 0.5. What is the value for each of the division or each of the square box? We take 0.5 divided by 10 divisions. It gives us a value of 0.05. And we can estimate until half of the division. Then we take 0.05 divided by 2 and it gives 0.025. This means that for the values of y2 and y1 that we substitute into the formula of gradient m must consist of 3 decimal places. For the x-axis, there are 10 divisions between the values of 0 and 20. What is the value for each of the division or each of the square box? We take the value of 20 divided by 10 divisions. It gives us a value of 2. And we can estimate until half of the division. Then we take the value of 2 divided by 2 and it gives 1. This means that the values of x2 and x1 that we substitute into the formula of gradient m does not consist of any decimal places. Therefore, the values of y2 and y1 that we substitute into the formula of gradient m must consist of 3 decimal places, whereas the values of x2 and x1 that we substitute into the formula of gradient m does not consist of any decimal places. However, the values of x2 and x1 are in cm. We need to convert them into meter. Therefore, we multiply the x2 and x1 with a prefix of 10 to the power of negative 2. Then we use the calculator to calculate for the value of m. The value shown on the calculator is 3.928571,429. How are we going to transfer the values from the calculator to our lab report? Shall we write down all the 10 digits as the value for the m, or we round it off to 4, or 3.9, or 3.93, or 3.929? How to make the decision? For the operation of multiplication and division, the least number of significant figures of the x and y entries is considered and reflected in the calculated value of the gradient m obtained. The values of y2 consist of 4 significant figures and the value of y1 consists of 3 significant figures, whereas the value of x2 consists of 2 significant figures and the value of x1 also consists of 2 significant figures. Among the values of x and y entries, the least number of significant figures is 2, but 2 is slightly less, can be allowed to add one more significant figure to become 3 significant figures. Therefore, the value of m is rounded off to 3.93 seconds squared per meter, which consists of the least number of significant figures, 3. Roman 5. Determine the uncertainty of gradient del m using the Excel worksheet. You may access to the Excel worksheet on the desktop PC available in the laboratory. This is an example of a blank worksheet. How to determine the uncertainty of gradient del m using Excel worksheet? Step 1. Fill in the column X with the values of L. Then, step 2. Fill in the value of gradient m obtained from the graph. Step 3. Fill in the column Y with the values of t squared. Then press Enter. All the values of L, m, and t squared that fill in are in SI units. This is the value of del m calculated by the Excel. Please record it down in your workbook. Round off the value of del m to the same number of decimal places as the m obtained in part 4. The del m calculated by the Excel worksheet is rounded to 0.24 seconds squared per meter. Therefore, the values of m and del m obtained are 3.93 plus minus 0.24 seconds squared per meter. Roman 6. Determine the acceleration due to gravity. From the equation 5.2, the oscillation period t squared of the simple pendulum is given by this expression. Comparing it with the linear equation y equals to mx plus c, where the t squared is the y, L is the x. There is no y-intercept according to the equation 5.2 theoretically. Therefore, the formula of gradient m is 4 pi squared over g. Rearrange this formula to get the acceleration due to gravity, which is 4 pi squared over m. Then substitute the value of the gradient 3.93 into this formula. As a result, the acceleration due to the gravity is obtained as 10.0 meter per second squared. It has been rounded off to the least number of significant figures, which is 3. Roman 7. Determine the uncertainty of the acceleration due to gravity. The formula of the acceleration due to gravity is given by 4 pi squared over m. Based on page 2 in the Physics Practical Workbook, Deduce the formula of del G using the combination of uncertainties. Rule B. Therefore, the del G obtained is del M over M multiplied with the acceleration due to gravity G. Then substitute the values of del M, M, and G into this formula. As a result, the del G obtained is 0.61 meter per second squared. Therefore, the result obtained for the acceleration due to gravity for the simple pendulum at small amplitude, which is less than 10 degrees, is 10.0 plus minus 0.6 meter per second squared. The experimental uncertainties should be rounded to one significant figure, and always round the experimental result to the same decimal place as the uncertainty. Roman 9. Calculate the percentage of uncertainty. The percentage of uncertainty is given by del G over G multiplied with 100%. Then substitute the values of del G and G into this formula. As a result, the percentage of uncertainty obtained is 6%, and it is less than 15%. This means that the result that we obtain for G plus minus del G is acceptable. Roman 10. Calculate the percentage of difference. To find out how much difference the experimental value G obtained from the standard value G, 9.81 meter per second squared. The percentage of difference is given by this formula. Then substitute the value of G experiment and G standard into this formula. As a result, the percentage of difference obtained is just 1.94%. The second part of this experiment is to investigate the effect of large amplitude oscillation to the accuracy of G obtained from the experiment. The condition is fix the length of pendulum at 100 cm. Swing the pendulum bob through the large arch of about 70 degrees from the vertical and measure the time for 5 oscillations. The result obtained from the experiment is tabulated in this data table. Then use the equation 5.1 to calculate for the acceleration due to gravity for large amplitude oscillation. Substitute the value of the length in meter and the t squared into this formula. As a result, the G obtained is 8.09 meter per second squared. The percentage of difference that calculated is 17.5%. This indicates that the G obtained for large amplitude oscillation is very much deviated from the standard value of G, 9.81 meter per second squared, compared to the G obtained from small amplitude, less than 10 degree oscillation. Discussion. Roman 1. State the results obtained in the form of G plus minus del G meter per second squared, the percentage of uncertainty, and the percentage of difference for both angle 9 degree and 70 degree. Compare the values of G obtained and write your comments. Roman 2. State the possible errors occur in the experiment and elaborate them. Roman 3. State the precaution steps taken in the experiment. Last but not the least, the conclusion. State whether the learning outcomes or the objectives of this experiment could be determined by the experiment. A warm reminder, please check with your lecturer when to submit your experiment report, as your lab report will be evaluated based on the report writing skills scoring rubrics provided in the Physics Practical Workbook. This is the end of this video session. Thank you for joining me and have a nice day.